Delta G has a relationship to K and a relationship to Q based on the fact related to temperature. That delta G is dependent on temperature and K is dependent on temperature. And that we can end up relating them into this by delta G standard equals negative R T ln K. It doesn't matter what K value you have. Doesn't matter what K value you have, delta G is related to K. Could be KSP, could be Ka, could be just a regular K. So solubility is related to K. Solubility, the KSP, is going to be related to Gibbs. Your acidity and basicity is going to be related to Gibbs. All that can be measured. And we can relate that delta G standard, delta G non-standard is equal to delta G standard plus RT ln Q. Of course, you have to remember how to set up your Q, but we can look at this. So let's look at a simple equation that we know very, very, very well. We know that the water will naturally split up into, do we have two waters? Well, we'll just say one water. One water is going to split up into H plus and OH minus. H plus and OH minus. Aqueous and aqueous. This is our KW expression. Now, at 25 degrees, we learned that that's 10 to the negative 14. But maybe we want to find out what is the KW at let's say 45 degrees C. How does the KW change? And so for that matter, we have to find our delta G value. Delta G at 45. So let's find our H. Let's find our S. H for water liquid is negative 285.83 and S is 69.91. OH minus is negative 230 and S is negative 10.7. Then H plus, if I remember right, is pretty easy. H plus is going to be 0. We've artificially set this as 0 and 0. So to calculate our enthalpy, it's going to be negative 230.0 minus a negative 285.83. So you'd say, oh, the H is 55.83 kilojoules. Our S going to be what? Negative 10.7 minus a 69.91. So that's going to be what? Negative 80.61 joules per mole Kelvin. So at 45 degrees, which is plus 273, too far, plus 273 is 318. Delta G is equal to 55.83 minus 318 times a negative 80.6 divided by 1,000. 83. Okay. So you'd get a delta G of 81.46. Now with that in mind, 81.46. Delta G is related to R, T, ln K. Delta G, R is a constant, T is our temperature, ln K. So you could look at this as two versions. If you're given delta G, you're going to say delta G is over negative RT. And to get K, you're going to have the inverse log of both sides. But if you're given K, you could find our delta G. Given K, you could find your delta G. So in this case, once again, watch out for the units because R is 8.314 joules per mole Kelvin. 81.46 times 1,000 divided by negative 8.314 and 318. Then we're going to take the inverse log of that to find what is our KW at 45. KW at 45. 8.314. Our KW is 4.15 times 10 to the negative 14th. So C 460. Okay. So that would be our value, assuming we did everything right. Okay. 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 Yeah. Mm-hmm. So less spontaneous. Okay. Oh, how are we going to deal with this? Our non-standard. Our non-standard is if we have our given delta G and we have various values for Q, we can look at how this is going to shift. Now, this is maybe not the best problem, but essentially this looks at how our value has changed if one of our values on the Q expression has been changed. Now, this one, since we have a push-pull relationship already, to get back, we're essentially going to try to get back to equilibrium. So, like, for example, I'm going to flip it over. We said our delta G was 81.46. 81.46. What happens if, now keep in mind, what happens if in our equation we add a bunch of acid? We add, say, instead of, we add, let's say, 0.5 molar of acid. 0.5 molar acid. Now, typically, in most situations, 4.15 times 10 to the negative 14th, we should have 2.04 times 10 to the negative 7th of both. 2.4 if we split it up evenly like we would with most acids. But in this case, if I add some acid, the first thing that's going to happen before the pH adjusts is the concentration of this would shoot up. And then once it's reestablished equilibrium, the concentration of OH minus would shoot down. Because remember, like, for example, if the amount of acid was 10 to the negative 3rd, the amount of base would have to be 10 to the negative 11th. But before that happens, and then like an ICE table, the first step is acid concentration goes up. So how would that change our delta G value? Well, delta G is equal to 81.46 plus our R times our T, 318, times a ln of Q, ln of 0.5 times 2.04 10 to the negative 7th. How will that change our delta G value? Five times 8.314 times 318 by 1,000. So 2.56. You're adding that to 81.46. Our delta G not standard, which means it's not at equilibrium, has dropped down to 38.89. Meaning, if we look at this versus our starting point, what does that tell us? It becomes, this is wholly out of balance, and it's going to shift, really wants to shift back towards equilibrium. So okay. If, for example, it was at equilibrium, if this was 2.04 times 10 to the negative 7th, then this would be negative 81.46, and you'd subtract those two, and you'd get a delta G of 0. But because of this, it's positive. Our H plus and our OH minus, what's going to happen is it's going to shift backwards to form our water. That means this guy's going to have to go down a bit, and this guy's going to have to go down a bit to get us back to our equilibrium. But the fact this guy going down, since it's already small, is going to make a big change. But so that is just a quick example. This is not often used. This equation is not often used, but it's used to determine the actual state at a reaction point. Delta G standard is a physical measurement of delta G, like at standard state conditions, which means 1 molar. 1 molar of all values, which is not a typical situation. Not a typical situation, but it's useful for finding the equilibrium constant. Delta G standard delta G non-standard, which is delta G without the naught, is actual physical measurement of experimental data, where the situation is not perfectly one-to-one. So we use that more often, but I mean, this is maybe more useful in the real world. However, we will not use it so much.